Hey guys, this is a special edition of the Mavi siblings, specifically made for Morgan because she needs to learn a lot about statistics before this weekend. So what better way to do than a video? And Alex, feel free to watch too. See if I said anything blatantly wrong you don't think I did. You're lucky enough to have an older sister who is in fact paid to tutor in statistics. I'd probably give about 5 or so lessons a week, so this week it's just gonna have to be 6. And I'll give you more information, particularly pertaining to your experiment after you understand the basics. I downloaded the same video software that Morgan has and that I suggested to Alex, and I used the screen record thingy, and it was really cool. This is the normal curve. Most things in nature fall in a normal distribution. Most specifically, people do. In psychology, we use this all of the time. What you need to know is that the area underneath this whole entire curve is equal to 1, okay, or 100% of the population. The entire population will fall under that. This line I just put here is the mean. In populations, we call that mu, or in terms of standard deviation, we call it 0. There's my lovely 0. Okay, standard deviation, what is that? Well, I'm so glad you asked. These tick marks refer to standard deviation. 1, 2. Standard deviation is exactly what it sounds, a standard measurement of how the data scores deviate from the mean. So how much variance and variability there is between the scores, because as you can see, not all the scores fall within this nice middle of the mean. Some scores are all the way out here on both the extremes. So if we're naming these standard deviations, this is 1, this is 2, and this tick mark over here, wow, it's really hard to write like this, is 3. Accordingly, this is -1, -2, and -3. Usually we only draw the normal curve up to this far because technically this normal curve goes on out to infinity, but for practical reasons it really doesn't, because the percentage under the curve becomes so negligible that it doesn't even matter. They're called standard deviations because, like I said, they are standardized. So no matter what you're measuring, whether it's IQ or human height size or speed of a cheetah, the standard deviation means the same thing no matter what the distribution is. And the cool thing is that they already did the math for us, so we can know what percentage falls in this shape, between standard deviations in 1 and 2 without even doing calculus, which is awesome. At one point someone did calculus, but they have standard values, and most statistics textbooks have the values listed in the back of the book, so you don't have to do anything. Between the mean and the first standard deviation is approximately 34% of the population. Forgive my percentage sign. And if you haven't noticed, this standard deviation is symmetrical, which means between -1 and 0 is also about 34%. Moving on, right here between 1 and 2, 14%. And over here, 14%. Notice that even though this is on the negative side, it's still a positive 14% because we're concerned about the area underneath the curve, not these values. These standard deviation values are only in reference to the mean. So your mean could be 100, and then obviously none of these values will be in the negative. And this, between 2 and 3, we say is about 2%. Now, of course, these are approximations, enough that you can memorize it and take your stats test. Technically, there is a population percentage that's between 3 and 4, and between 4 and 5, and between 5 and 6, and all through the negatives. But like I said, they're negligible. The best example I can use, especially for you, is that of IQ scores. Human IQ tests are designed especially so they fit this beautiful normal curve. Okay, the average human IQ is exactly 100. And the standard deviation is 15. So mu of the population equals 100. Oh, geez. And the standard deviation, which is represented by a lowercase sigma, is 15. Now, if you recall, this first tick mark beyond the mean was +1 standard deviation. So, what's the mean plus 1 standard deviation? 100 plus 15 is 115. Awesome. Accordingly, the next one is 130. And if you know, if you remember that there are about 2% of people that are going to fall in this area right here. And those are the people who can get in Mensa. You need to have an IQ of over 130. And if that means 2% of the population, that means 1 out of every 50 people you know could be in Mensa. But our family kind of skews that just a little bit. Don't tell YouTube I said that. And then following that 3%, or the third standard deviation is 145, which means there's only a very, very small portion of the population with an IQ over 145. Then the same thing happens in the negative direction. This standard deviation of -1 is equal to an IQ score of 85%, or of 85. And this is 70. And the last one should be 55. Oddly enough, you, Morgan, know several people that fall on both ends of the spectrum. Your cousin Charlie would be down here, and I know for a fact that your brother and I are up here, both in the negligible portions of the population. Let's just review the population information we do know. So, we know that these two sections are each 34% of the population. So 34% of all Americans have an IQ between 100 and 115. 34% of Americans also have an IQ between 85 and 100 IQ points. We know that these sections out here are equal to 14%. So 14% have an IQ between 150 and 130, or 70 and 85. And finally, the last sides are the 2%. Okay, but what happens, let's delete these, if someone has an IQ score of 120? Right here. 1, 2, 0. That doesn't fall evenly on a standard deviation, does it? It's not +1 and it's not +2, it's somewhere in the middle. But because this curve, the curve is curved, we can't just do a simple mathematical formula to figure out. We can't just say, okay, base times height divided by 2. You know, like, it's not a triangle. Alex and I know that from calculus that we have to integrate this. Fortunately, a bunch of mathematicians already integrated it for us, and there are charts in the back of one's book. So, in addition to standard deviations, what we have are called z-scores. And they are just a bit more specific than standard deviation. O-R-E. There is a formula for z-score. Z equals x minus mu all over sigma. Okay, so this is a formula for a z-score. So if we have a raw score, that's what we call our data, and for you, that's going to be the numbers 1 through 9. Those are going to be the raw scores of the tastes of your cakes recipes. So we have a raw score of 120 in this example, and we want to know how the person fits in with the rest of the population. Exactly. We don't just want an approximate, oh, you fall within this 14%. No, we want to know exactly. So we take x, which is the raw score of 120, subtract mu, so mu is the mean, which is 100. That's going to give us 20 over the standard deviation, which is right here. The standard deviation is 15. So 20 over 15 equals 1 1/3. So in this case, it really is exactly a third of the standard deviation right there. Then in stats books, what happens is you can look up numbers in the back and you can calculate exactly what that percentage is in between that person and the high end, or the opposite. How much, or the percentile is actually what it is, and that's all the people that are below that score. So when you were growing up and you were in the 99th percentile of height because you were 3 feet tall as a 4-year-old, 2-year-old, whatever, percentile is how much of the population you are higher than. So people with IQs here are in the top 98 percentile, just to let you know. So now that you know about the normal curve a bit, first of all, z-scores can also work in the reverse way. Using tables, if you want to say, oh, I want to know what IQ score makes a person in the 33rd percentile, well, you can then look up a percentage of 33, area under the curve, and it'll correspond with a z value, which will then put you in a frame of reference with the standard deviations. I want to move on to hypothesis testing, though, because that's what your whole thing is going to be. Now let's see if I can do this without screwing up. So we have one population that's normally distributed. I want to edit, copy, and paste. And I want to paste it clear. Aha! I'm so smart. All right, let's say this orange curve, right? You see it's the full curve, represents the population of college students that there are in America. And we're plotting their GPAs. So let's say right in the middle is a GPA of 3.0. And we can make our standard deviation, 0.25 maybe. So that would be 3.25. 3.5 would be over here. And this would be 2.5. And, College Board took a census, and so they know that this is, in fact, the data for all of college students in America, and not just numbers I made off the top of my head. All right, now this population over here is us at UM. Okay, so let's say that I took a sample of 100 of my classmates here at UM, and I plotted their GPAs, and it also came out normally distributed, which is a good thing. That means I did my random sampling properly, and we like things to be normally curved. And I see a discrepancy like this. See, there's a big difference. In fact, there's a name for that difference. It's called effect size. That falls right in the middle. What a hypothesis does, technically, is it compares the mean of this population, which is 3.0, to the mean of this population, which it looks like 3.25, and says, hey, look, there's a difference. But they want to figure out exactly how much of a difference there is, and if the results are statistically significant. What statistically significant means is that our sample population, the green population, could not be randomly selected from the actual population, the orange population, by chance alone. Obviously, if there are 3 million college students in the United States and I only used 100 of UM students, there's a very, very large variance of what the mean could be. So in this case, our UM GPA fell at about 3.25, and we want to know whether that means that on average UM students have higher GPAs than the rest of the country or not. What we do then is we compare the difference between this mean and this mean, given what we know about standard deviation and the numbers we have. In the case of this experiment, I said n equals 100. I had 100 UM students. And there are some formulas that you can go through, and you end up with a final value, which is, if we're doing z-test, is called your z obtained, and then you compare it to some charts in the back. And in the charts in the back, we can look up what's called an alpha level. So if I look up an alpha of about 5% in the back of the book, let's say, because that means there's only a 5% chance I made a mistake. And then it's a 95% that I'm correct, which is good. And it will give me a corresponding z-value based on how strong I want my experiment to be. And I just compare the two. If a value that I obtained for this green population is more extreme, which either means more positive or more negative, then I have a significant difference. And that means that something between these two populations varies. That means this population, this sample could not possibly have come from this exact population. That means the independent variable, in this case, which college you go to, had to make some sort of difference. And it wasn't through chance alone. This 5% says that it was only a 5% chance that it was just the random draws. They just happened to draw more people with 3.5s than 2.5s. But 5% is very little. So 95% likely that there's a difference between these two populations, that yes, UM students have higher GPAs than the average American students. In the case that my obtained value is not more extreme, then I have to accept my null hypothesis, which means, oh, there's no difference. I could have randomly drawn these 100 students and gotten that mean of 3.25 by chance alone. So Morgan, let's talk about this as it refers to your chocolate cake experiment. First thing we're going to do is we're going to take the 50 scores of the original cake that had no substitutions, and we're going to plot them and find the mean. You know, let's say it's about 7. It's pretty good. It's not the best they've ever had, but it's certainly not just mediocre either. So then we are going to plot another one of your sets of sample data. So control copy, control paste. Let's say this is the recipe that doesn't have milk in it. And let's say that those scores, the rating of the taste, look like this. Well, as you can see, there's a difference. So that means I can run that statistical test like I just talked to you about and see whether these two, in this case they're the entire population, you tested the same 50 people 7 different times. So I just compare the two and see if I have statistically significant results. Also, let's say this is the Splenda experiment, okay? And that one falls way further down. That one has another mean, right? All of our means are here. I should have drawn them. Say the Splenda cake only gets like a 4 rating, and then the average cake, or the standard cake, gets a 6 rating, but the milkless cake actually gets 7 rating. So we're going to compare the milkless recipe and the sugarless recipe to the original recipe. So what we do is we run the numbers through the test and we decide whether those tastiness ratings could have been chance alone, or if it means our independent variable, which in this case is the ingredients, actually changed. So this concludes your first taste of statistical analysis and hypothesis testing. I'll just let you think about that and digest that for a little bit. Oh my gosh, so many baking and eating puns. And then maybe I'll post another video explaining in a little bit more detail what I want to do with your specific data. That's it. I'll see you later, and good luck eating chocolate cake.